Hi guys, can you hear me?
Yeah, we can.
Okay.
Well, after all, we are half the class, so. Thana,
Yes. Go ahead.
just so you know, I'm not feeling well today, so I'm probably gonna be going home partway through class, unfortunately. Just while
Okay.
I'm it.
Okay. Okay. So let's start. I think we have Philip and Nolan. Are they hiding around? No. So I need to make this announcement that if I don't, whatever assignments I don't receive, that's Philip. Right. By end of this week, I need to start reducing points because
By
it's
the end
been
of this
due.
week.
Yeah. That you'll start losing the maximum, like 20% per week.
Is that like by Friday or by Monday?
At least by Friday, but latest by Monday,
Okay.
right? And next week is spring break, so so you'll have to do your exam sometime during spring break. I'll send it to Stephanie, and then you can schedule it when you come back or before spring break, and that will include everything up to chapter 3,
Okay.
right? So before you do the exams, the midterm, I would recommend that you complete the assignments, right? So as I was saying, Nolan and Philip, that any assignments, it's been due like several weeks now. I know you have submitted some, but those who have not, you'll have to start really losing points now, right? And the midterm, you'll do it. So I'll have to stop for the midterm because I don't know it'll work because of the different schedules, and I don't want to go back and teach. So I'm going to assign you some programs to do, homework and midterm, and complete all the assignments, right?
Okay.
It's
So
a long,
basically,
Sounds
get it
good.
done by Friday, or we're losing points, right?
yes, Monday. I'll make it Monday easier for you,
Got it.
right?
Got it.
But not the one I'm going to post this week.
All the past ones.
All the past ones,
Okay.
right? So I'm going to post one on hashing this week. So let's actually complete this topic called hashing. Right? It's now that we know what hashing is, the next thing would be, now we know how to get a hash code for a key. Right, so we know we essentially, one of the troubles we were having was how do we translate a non-number to a number? Because if we can get the number to an integer number, then we can create an array. If the key can be translated to an integer, a positive integer, then the integer can be converted to a right, converted to a number, index of an array. The next question is that, okay, even if we do that, like for example, these things can get, like for example, if we do that, then what happens is that multiple keys can get hashed to the same index. And because there's now no guarantee that the key, it'll be nice if we can have a one-to-one hashing, but otherwise multiple keys can get hashed to a same index. So first is the concept of what is a hash code, which is to convert the key to a number. Second is modularized hash code, meaning, well, it's a number going to be between 0 to 2 billion, but we don't need 2 billion. So we modularize it. To modularize it, we divide it by a prime number of the size m, that's the size of the array, and take the remainder. So modularizing, so you take the mod of the hash code, which gives you a number between 0 and m minus 1, right? So we take that each so the question is, now there are different problems related. Do you know what the birthday problem is? Never heard of it?
Isn't it just like that's very likely for two people in a group to have the same birthday?
Yeah. So how many people do you have to have before you find that, well, two people have the same birthday? And it's not a lot, even though there are lots of days, it's not a lot before you find that the probability of two people having the same birthday is actually more than half quickly. Right? So that means they're going to get hashed. If you were trying to hash the people based on birthdays, then they're going to get hashed to the same location. Right? So the opposite of that is how many, like another problem is called the coupon collector problem. What that means is how many, like, there are those things that say you collect 5 coupons from this, and then when you collect all 5 of them, you'll win whatever you have to win. So how many boxes of cereal do you have to buy before we collect 5? And that's what the coupon problem is. Right? So based on those, actually there are easy solutions to that. You find that essentially you need to, we may have to end up having arrays that are extremely large to avoid hashing to the same location, which is not very effective. If you're going to hash them to 2, if you're going to create an array which is 10 times larger than the number of required slots, that's not very effective. So an easy solution would be combine what we have learned, arrays and linked lists. Right? So what we do, this is called separate chaining. And what we do is we create an array of linked lists. Right? So we create an array of linked lists and multiple. So if a key gets hashed to the same location, we link it to a list that's associated with that. Right? So it's not unique. I mean, the hash coding in each location may have more than one. And if multiple things get hashed to the same location, we just keep hashing. We just keep adding a linked list at that array location. Right? It's a pretty straightforward solution because you just create a linked list. I mean, we know that we can create a linked list, and then we create the linked list and connect it to the array. So we have something. For example, because if you see this, A and E gets hashed to the same location, and they have the same hash code. A has a hash code of 0, E has a hash code of 0, so they get maintained as a linked list on that number 0. Right? So A has a hash code number that's 0. E has a hash code number that's 0. Of course, if you have multiple A's and E's that show up in the key, all we do is we update the key, update the value, but keep the key in the same hash location, right? The symbol table. So we update it and then. Similarly, if you look at M, R, C, H, and M have the same hash code, so they get hashed to the same location, and all we do is create a linked list over there. Right? So that's what's called separate chaining. And there are different ways, there are multiple, they're all based on the same idea, but there are different types of hashing we can do. Right? So this is the implementation. Of course, it's pretty straightforward. All we do is create an array of hash keys, array with the modularized, where's my pen? And then if you're going to get something, get the hash code first, right? Get the key, find out the hash code of the key, right? So find out the hash code of the key and then keep iterating on that location. Go to the location that's the symbol table ith location, because ith location is where if you find it, it's going to be there. If it is not in that hashed array location, it's not there. Right? So if you're going to look for something, so if you're going to search for the key, now we're going to do two things now. We're going to search based on two separate criteria. First, the hash code. Right? So you need the hash code to get to that location. And next, the equals method. Because equals, so within the hashed locations, we have to see which of the key is equal to the key we are trying to search for. Right? So there are two criteria that's being used. One, hash code. Second, key. Equals method. Right? So this is why they say that if you're going to, like they say, when you overload the equals method, you also have to overload the hash code method. Right? Because if you overload the equals method and don't overload the hash code method, what would that result in? Go ahead, Philip.
Does the default equals like assume that if the hash code is equal, then they are equal?
So default equals is just the object reference number. Default hash code is the object reference number. Right? So this is a symbol table.
Oh.
So there's a key and a value. So every time we generate a new object of the key, they have to equal. They have to be this. They have to override the equals so that the two different objects of the key end up having the same equals value. Right? For example, strings have that property. Strings, if you use strings as a hash code, that's okay. Oops. Right? If you use strings as a property, like if you use anything, right? Like 1, 2, 3, ABC as a string, then the hash, you can create multiple instances of the same string. And we know from Java that if you create two different strings, but they're not considered equal in the sense of equal. They're two different objects, right? Two different objects, therefore they end up having two different hash codes. But the equals method is overloaded to make them equal. Right? So that's what we use as a key. Right? We are going to overload the equals method to make sure that if two strings have the same identical characters, they will return 0. What happens if we don't overload the hash code? What will happen? What would happen if you are using keys, you're creating a hash code and using keys, but you forget to overload the hash code for the keys?
Will the hash code just be like the object reference number, so it doesn't actually reflect if like the values are equal?
So by default, the default hash codes are based on the actual reference number. So every time you generate the same key object, they'll have a different reference number. So if you use that hash code, you'll end up looking at a different box, a different location. Right? So you put it in one box and search for it in another box. Because first time when you inserted it, you were using a hash code to place it into one hash location. And then if there are multiple keys, you would actually append them using a linked list. Multiple values at that hashed location. When you're trying to retrieve it, first you must identify which box it is in. Right? So if you think of hash codes as boxes, so first you need to look at which box is this going to be in, and then you must search inside that box to find the matching key. Do you see it? Do you see that if you're going to use keys, anything, especially for things like hashing, you must override the equals method and you must override the hash code method. If not, it will not work. Right? It will not work because the mechanics of locating a hashed key is first we need to identify what the hash code is, so that we have an array of locations. We need to first identify which array location we need to go and look inside. That is based on the hash code, and then we look for the item that's a linked list over there. Right? So this is the warning that you would see, that when you're overriding equals, they say, well, what happens if you try to overload this use it as a key? So, but the search method is pretty straightforward. All we have to do is write a loop. Right? All we have to do is watch the recordings, Justin.
Yes, definitely. Thank you.
Okay. You go through the key. So this is a simple, straightforward linked list thing. Right? Start from the head node, go to the node that's at the head of the linked list, and then until you hit the null, which is the end of the list, keep going. If key dot equals x dot key, return, else keep switching to the next thing. Right? That's a simple linked list thing that we do. Right? So how do you think insert is going to be? What do we do for insert?
We hash the thing, and then we go to the box which corresponds to that hash, and then tack that item onto the end of the linked list.
Yes. Before we attach, we need to look. Before we attach, we need to look if the key already exists. So we really have to go through the entire thing every time, right? We have to search through the whole thing to see, okay, if the key already exists, then we update the value. If not, we add it to the top of the list. Okay? That's what the put here is doing, right? So if you look at the put method, that all it's trying to do is that we identify the hash code, start at the node, and then the first thing is to keep looking. These two lines is to see that can we locate the key within that list. If we can locate the key within the list, then update the value and return. If not, if you have reached the end, then create a new node and add it to the top of the list. Right? So if you locate the key within the linked list, all you're going to do is update and then return. Right? If not, update it. Right? For all the things about hashing is pretty easy. I mean, people kind of look at it. Oh, you haven't learned hashing. So what? Hashing is just arrays. I mean, right? I mean, but hashing is like you're going to learn a big secret or something that's so important. No, it's not, I mean, something so difficult. It's not. It's pretty straightforward to create hashing because it's just an array of you're trying to get the best of arrays and linked lists together. Right? So use the arrays and linked list so that your list doesn't get too long. Convert the key. That's essentially what it is. Right? So the only trick we have to do is, so we would find that, so we have to, right? See, this is based on some empirical analysis that usually you want to keep. So of course, the average, so the average size of a linked list is pretty straightforward to determine. If there are n items, and if there are m hashed locations, then the average size would be n over m, right? If everything gets distributed nicely, it's n over m. So the rule, a typical rule of thumb here is that don't make it too long. So if you know the number of items, let's make the keys, the chains to be not very long, anywhere between 3 to 6, but in approximately 5. Typical choice is to make the linked list size to be somewhere in the 5 range. Right? So if you need to choose the size, and one of the assignments I'm going to post next time is that you need to hash all the assignment is this, that you have the hash the entire dictionary into a hash. There are about 80,000 words, I believe. Right? Create a hash all of them into a hash key. Right? Put them into any type of, maybe a separate chained hashing structure. So you have to create, so typically you'll have to use something like a 20,000 size array, but 15 to 20,000 as the size of the array, and then hash the locations. And the homework is that, so when you type in, as you're typing, so it's a spell checker. So if you type a word, the first thing it'll do is have you type, if the word is spelled correctly, it'll hash it and locate the thing and says you don't, that, because if it finds a word in the hashed keys, then you know it's spelled correctly. If you think that it's not, if you find that if you cannot find the key, because every word is a key, if you cannot find the key, your program has to suggest something. Right? The program has to suggest something. So one way to, how would you suggest a word when they mistype something?
Well, if you spell the word like a little bit wrong, I guess the hash would be similar, wouldn't it? So you'd look at like a few hashes. No.
No, it won't be. It can be far away. Even if you miss it by one, it can be far away. Right?
Do you look for hashes that are within like a certain range within the hash of the word you spelled wrong?
But that's why the hashes won't be, the hashes and the misspellings don't really kind of cluster. Right? So let's see if this thing works. I'm suggesting something to say, what happens if you kind of exchange, like let's say you're typing and you miss something, or you mistyped it, you interchange the characters. Right? Can we switch characters around and see whether by switching we can identify a word?
Yeah.
Right? So we switch them. So we take the characters and try switching them one at a time, and see, switching them gives us a recognizable key, a word, or adding something to the beginning of the word, adding something to the end. Right? So certainly we can have any type of a rule that is, if someone types it like this, that we can switch. Let's try the simple rule to say we'll switch characters, or add a character to the beginning of the word, or add a character to the end of the word, or remove a character, or do some simple rules like this, a set of simple rules, and see whether any of those rules get you to a valid word. right? And that's done because we have to switch those characters and rehash it to see whether the rehashed word ends up being in the dictionary. So that's one way of doing it. There are many ways of doing it. Of course, we can if we learn more string structures, we can see how does we can kind of go along a tree-like path and see what's adjacent to it. Right? But hashing will not give you the adjacent word. Like switching to looking around that clusters will not get you the hashing, because even if one character changes, the hashing can be somewhere else. It can be hashed to a different location.
So to do this, it's going to take like if you're saying try for adding a character at the beginning, that means you have to try for every letter and hash it, check it.
Yes,
okay.
right?
Okay.
Yeah. So there are a few rules. Like you will add a character to the beginning, add a character to the end, switch each pairs of characters, and see whether we find something like that. Right? Now, hashing is a pretty way of solving anagrams too. Right? You take the characters and hash it in every possible way and see whether you can solve it, right? Because you can easily try out every possible combination. It could help you solve it. So that's one way of doing hashing. And of course, the times is that if you compare the red-black trees to the other types of trees, separate chaining. And these are right. So these are based on average cases. So it's about 3 to 5. An average case, if you can create a hashed code, then your number of lookups is going to be about 3 to 5. The worst case, by probabilistic reasoning, it turns out to be log n. Right? The worst case is log n. The average case is 3 to 5 if you create a hash code. Compared to red-black trees, it's not too bad. Right? This is about 2 log n and log n. We know why it's 2 log n, because each path can be, because the red-black tree, it can be alternating red and black nodes. So therefore, the worst cost is 2 log n. The best cost would be log n. Right? This is going to be log n 3 to 5. So hashing is actually pretty good. Right? In terms of performance, it's pretty good. And that's why two things about hashing. It has a good performance, and it is also very easy to implement. Right? It's not a complex structure like a red-black tree where we have to keep rotating and doing other things. It's pretty straightforward, easy to implement, and the performance is very good. Right? But however, it's missing something that's very important. This thing, that's we are just saying, it doesn't give us ordered iteration. We cannot pull out a hash code and start listing out the keys in an increasing order. Right? So it does not give us an ordered iteration. That's the problem. Like sequential search also does not return an ordered thing. Whereas binary search trees and ordered arrays and all these things will give us ordered operations. And also remember that sequential search works on equals, hashing works on equals, all these three works on compared to. Less than 0, greater than 0, and equal to. So we use the compare to function to insert and retrieve keys. So that's one implementation of hashing. So there is another type of implementation and combinations of this is what's called linear probing. Right? So linear probing is based on the idea of we use the array to be, we don't create a linked list. It's kind of like we're going to use an array, but we are going to not have a linked list associated with it. It's kind of like, let's say, when you have, these apartments, when you have a row of houses and then everyone has a car, and where do they want to park their car?
Right in front of their houses.
Right in front of their houses, right? So that's where you want to hash it. You want to put it right in front of the house. And you can only park one car in front of each house. What if people end up having multiple cars? Or if you end up having multiple cars, then what do we do?
Well, you could have a garage, but
No, you can't park in the garage. Your visitors are coming in. They're going to park outside. So what do you do when you don't when your spot in front of your house is occupied?
You have to find another spot.
Where?
The closest one you can.
Find the closest one you can. Right? Keep driving forward. Keep driving forward until you find the next empty spot. Right? That works too, right? So, and then of course, if you end up going all the way to the end, and if everything is filled up, go around the block and come back and start looking from the beginning. Right? That's what linear probing is. Right? So essentially in linear probing, you create an array that's large enough so you're going to put everything in an array. Create an array that's large enough for the number of items. So you need to have more spaces than the number of cars. Otherwise, people won't be able to park. Right? Unlike it's like New York or some place like that, they park a car on top of the other car. But in other places, you'll want to park it on the head of it. Right? So you need to have more spots than the number of the array locations have to be more than the number of items, and you create an array. And the basic strategy is that we'll hash it, find out the hash code, and see if that spot in front of your house is vacant. If it is not, look for the spot that's the next nearest spot. Keep moving forward. So you don't want to go back and forth. Just keep moving in one direction until you hit the end of the block. And if you don't find anything, you come around the block and start looking for a space. Right? That's the basic idea of hashing. So for example, this is what's going to happen. Let's say we are going to hash things, and we're going to hash A. A goes straight into that hashed location because initially all the arrays were empty. Right? Then B is hashed. B comes and looks. If B also gets hashed to the same location, then B finds that that's filled. So it moves one spot and then parks the car right there. And then we look for C. Well, C is lucky. That was vacant. So C parks it right there. Look for D. Where is D? D is also lucky. It gets parked. It can park it there. Then E is lucky. It gets to park right there. Then look for F. Where is F? F needs to park at the same spot where E is. So it drives a little one space forward and parks it there. Then G comes. G needs to park here, but that's taken. It keeps driving. The next spot is taken. The next spot is taken. The next spot is taken. So it parks like 4 cars away from where it needs to park. Right? That's what linear probing is. Right? So you park, and then H will park wherever it needs to, and then I gets to park there. So I moves a little forward, and then I parks there, and then J starts here. No, it's all taken, so it moves all the way, keeps driving all the way until it finds an empty spot and then parks there. Right? K parks here, L parks here, and then not there, so it moves up there, and M parks there. Now, of course, if M had hashed this, let's say for example N hashes here. Let's say O hashes here. Then what it does is, no, this is taken, so it drives forward and then comes back from this side and parks it right here. That's where O would go. Right? So you go to the end and then you come back and start parking in the vacant spot. So if you were going to locate something, if you're going to search for an item, what would you do?
We first hash it and then look for where it should be. And then if it's not in that spot, keep moving down until we find it. Or until we come back to the same spot.
Any improvements to that? Well, it kind of works, but it's possible that the key did not exist. Someone took your car and went away. It's stolen. So what do we do now?
If you go all the way around, like back to the initial spot, and you haven't found it, the key isn't there.
But do we have to go all the way around?
Or just the first vacant spot.
Yeah, we can stop at the first vacant spot. Right? We can stop at the first vacant spot, because if the car was there, then it would have been in that cluster of cars. Because whoever who parked it wouldn't have skipped that vacant spot to go somewhere else. So because you didn't find that car, because
but that would only work. That would only work if you're like you're not supporting like a delete operation, right?
That's my next question. Yeah, okay. That's my next question. If that's the case, then what happens when you delete?
Well, you can't tell apart the null spots that were null when you inserted and they're null now when you deleted. So
yes,
I think you have to all the way around.
Like, yeah, when you came, that spot was taken. Now that you parked it like three, 4 cars ahead, but your neighbor pulled out his car, so it has a vacant spot there. You might stop looking. Right?
So can we find a way to shift them back?
Yes, that's what we have to do. Right? So we'll have to shift them back, and the way to shift them back is wake up all your people and say, all those people who are clustered together, wake them up, ask them to repark the car again. Right? So once you remove something, and if it is in a cluster of cars, we'll have to wake up and say, maybe this guy should not be parked ahead. He should have been behind me, but he parked ahead of me because he didn't find the spot. So you need to wake up everyone who is downstream of you, and then ask them to go ahead and repark the cars again. Right? So a little bit of involvement needed there. And that's what they do. I mean, if you're going to park it like this, it's very, I mean, that's the only way you can make sure that, otherwise, after some time, if you don't ask them to repark it, like move it back or shift these cars around the cluster, if you're going to you'll have to end up at, once you keep using it, after some time, the hashing is no good. It becomes an unordered list. Right? It almost becomes an unordered list. So you'll have to keep looking all the way again and again, because every time you want to search for something, you'll have to go through the entire block. Right? So that's the basic idea of hashing, linear probing. Right? The key for so the put is easy, right? The put is easy to implement. You do the same thing. Start from the location and then where you want to park your car, where you want to insert the element, and then if that's not equal to null, right? If that's not equal to null, keep moving forward, right? Keep moving forward, and then if you hit the key, you break, right? If you hit the key, you up, right? It's there, so you can update it and you break it, like that. So if you hit you keep moving forward until you hit the key, and then you update the key and update the value. So there are two things can stop you. Either you hit the null, which is by this condition, in which case you're going to stop looking for further, or you find your key. That's the second case, right? So this is case number 1, where you hit the null, and this is case number 2. Either way, you will stop looking. You'll update. If it is a null spot, update the key and the value. If it is a key that's equal to the key, in this case, you're updating the key and the value, because updating the key doesn't make any extra, because you're updating it with the same value, right? You're updating the key and the value. So you keep moving forward until you find your car or you find a empty spot, right? And what's this stuff here for? The last thing on this side. We do I++. What are we doing over there?
That's to make sure we loop back around when we get to the end of the array.
Yes, right? So we move back to then, right, and start at 0 again, because when I plus 1, we keep incrementing I, and when I plus 1, I, and when it hits M, right? So M mod M is 0, then it turns back to the beginning of the array. Right? That's what we do there. Right? Get is the same concept, that you just keep looking until we have to go around the block, or you hit until you hit the null. If you hit the null, if you hit your key, or if you hit the null, if you hit the key, return the value. If you hit the null, return null. Right? Delete would be make it null, take all the things that's ahead of you and rehash it. Put them back into the hash code. Right? So that's what hashing is. Right? So approximately, if someone is interested in studying cars parked on a block of streets, you can. Right? And people are crazy about studying all types of things. You get a research and says, what are you trying to do? I'm trying to see how people park their cars. Now, so if the number of, when the block is half full, the mean displacement is about 1.5 cars. Right? And if the block is full, the mean displacement is about pi m over 8. Right? So when you have the array size to be almost, so it kind of varies. If you have an array size, it makes sense. When you have an array size that's much larger than the number of items, then you don't have to have lots of spaces to park. But the array size is almost equal to the number of items, then you'll have to start walking quite a bit. Right? So that's what the mean displacement is. So both types of hashing is pretty easy to implement. There are, of course, other various other improvements or suggestions to improve on it. There are different types of hashing, but they're all based on the same idea. Based on the same idea. So what about linear probe hashing? The worst case is still log n. As we saw before, the worst case when it comes about square root, but the worst case, this is probabilistically worst case about log n. This depends on the size of the array, right? And you want to have something about 3 to 5 cars. Again, ordered iterations are not possible. Right?
So,
Go ahead.
so wouldn't linear probing be a little bit worse in the worst case because we have a bigger array?
Yeah, right. So linear probing can be. So you want to choose a size that approximately will lead to that.
Right.
Right.
But then in exchange for a bigger array, we don't have to use another linked list.
That's right. Right. So it's a space versus time trade-off. And if you have a large array, then we don't have a lot of lookups after that. So now, are there any other types of hashing we can do? Like for example, there are other types of hashing. And before that, actually, people even actually use hashing, right? People try to do a denial of service attack based on hashing. So the good thing about hashing is that pretty predictable in terms of you can create the hash size, you can create the array locations as large as you want, and almost make it like an array. Right? I mean, it is almost like an array. We could have used an array just to begin with. The only reason why we couldn't use of course, all of us like arrays because we can pick and get and insert things right away. The only reason why we couldn't use an array is the fact that we couldn't convert all keys to an array index. I mean, that was the problem, that we couldn't use arrays. If all the keys were always numbers and tightly packed numbers, we could have always used arrays and not worried about anything else. Because keys were not numbers, that we had to go to this hashing. So it then brings back the same array type of thing again. So there is a little bit of issue with Philip's frozen in time. And he's disappeared. And you first freeze and then you disappear. Okay, so the thing is, if people actually try to use denial of service, right, because the some of the load balancing, meaning the way a computer, like when you're sending multiple requests to the same web server, right? Like so Yahoo, for example, Google, all these web servers have multiple servers. Right? You can be really serving all your thousands of queries per minute or per second in one web server. Right? So what they do is they do what's called a load balancing. Load balancing based to, they have like 100 servers, and then each of them is kind of like a call center. The call comes in, and then you pass the call to an available server. Like it automatically gets moved. Now it doesn't get served at the main office. It gets moved to the next one of the available call persons. And that's what they do. That's called load balancing. And load balancing is based on hashing. So they take the incoming request and use a hash code to determine which server you want to distribute it. So you want to get the loads and then distribute it to the, you have, instead of trying to look and see who just peek and say who is the next available person. Well, we can do that. Alternatively, we can take all the incoming hash codes, right? So incoming request, hash it with a hash code, and then send it to that counter. Let's say we have 10 counters. So every person, every request gets hashed to a location of one of the 10 counters, and then your hash code is 7, go to 7. Your hash code is 6, go to 6. Your hash code is 5, go to 5. Right? So that's a way of balancing the load. Because there'll be an array of servers, and then you put it into one of those buckets, and then so you go and stand in line behind that person on that counter. So when you have 100 servers, or several hundred servers trying to serve, right? So what they try to do is so if you know how the load is being balanced, if you know exactly what the algorithm they use to balance the load, you attack that by giving the same hash number. So it ends up that all your people are lining up behind this one or two people. And those servers now become unable to serve any valid customer. Right? So the hash code, how you do your hashing, is also pretty secret. You don't want people to find out how you distribute your load inside your clusters of servers. Right? Of course, the uniform hashing is important in practice because all these things, ACK traffic controller, nuclear reactor, pacemaker, they all are kind of like real-time things, which need a predictable, a fairly reliable response time. Right? So when you say real time, that means if something needs to be done at 9, of course there is nothing called 9 a.m. Is 1 second after 9 considered 9 o'clock?
Depends on how specific you want to get.
Yeah.
So how specific can you get?
I mean, I'd say it's 9 o'clock. And if just every day is a couple minutes after 9 is still 9 o'clock.
For us, it's okay. Right? Not for everyone.
Well,
No.
yeah, if it's like a scheduled thing, then yeah. But if you're just like, what time is it? And it's like 9:02, you say 9.
Well, then if we're talking nuclear reactor speed, then
Then you need to be a lot more accurate.
how much more accurate? Because there is nothing called 9 o'clock anyway, right? I mean, certainly it's a point. You'll have to choose a little time interval and call that 9 o'clock, right? But the time interval is in nanoseconds tolerance or microseconds, right? Small, few nanoseconds, microseconds. But if the tolerance is in milliseconds, that's not good enough for real time. Like if you're 1 millisecond late, now that's too late. You're not a real-time person. Right? So real-time situations require something more predictable, and these types of hashing gives you that predictability. Right? You could build your programs, you could choose the array size, you could do things like that, and you can almost exactly get that predictable tolerance in it. And there are other things, right? And again, this is like prime time, computation of prime time. That's a business. People want to find out how you compute. Coming up with new random numbers is an important thing. Like that hashing is also one of those things. Certainly there are other things. Now, what are these one-way hashing functions? How is hashing used in cryptography?
Are your passwords hashed to most websites where you have like a login?
Yes, your passwords are hashed, right? And they're one way in the sense that you can take your password and hash it to something, but you cannot take your hashed one and then retrieve your password. Right? So if you call, let's say for example, you forget your password, and you say, "Oh, I forgot my password. Can you give me my password?" They'll say, "I don't know what your password is." Right? A good web server should not save your password, and because people can either people can hack into it and find out what your passwords are. Alternatively, there can be some employee who is stealing passwords. I mean, if it gets stored in a password, you can certainly it's compromising security. So you want to save the password without storing the password, right? So you want to save it without storing it, and that's what hashing is used for. And you try to come up with those one-way hashings. So you take your password, hash it, and you don't have to modularize it, hash it. You can hash it to a number. It doesn't have to be a number between 0 and 2 billion. It can be a number between 0 and whatever big number you want it to be. It can be a long number, right? Instead of 10 to the power 9, it can be 10 to the power 18, or even larger if it needs to be. So when people type your passwords, so when you retype the password, how do they know that you typed it correctly?
They'll hash what you just put in and compare the two.
Yes. Right? So you'll hash again what you typed in, and if the hashes don't match, then you didn't type it correctly. Right? So that's how a real web server should save the password, because the password should not be saved the way you type it in, because that's something that's readable. So if you hash it and save it, and every time you type in your password, the password is hashed and compared against the saved hashed password, and if they are the same, you type it correctly. Right? So that's how they use that. Right? And also now you want to have their one-way hash function. And it is possible that two keys get hashed to the same thing. It's very, very unlikely, but it's possible that you may be able to type something wrong and end up in the same hash. Right? Well, yeah, so many things can happen. Right? It is also used in like digital like for example, message digest. What is a message digest or a digital fingerprint? So let's say, for example, I'm going to give you. I'm going to write your transcript, right? Give it to you in a document. Is it possible that you can alter the transcript, a digital document? So how do we prevent that from being happening?
I don't know if this is the right answer, but you could just hash the whole thing.
And hash the whole.
You hash all of it, and then when you get it back, you compare to see if it's exactly the same.
Almost like that, right? So what they do is they take the entire document, come up with a hash number, and they print the hash number right below on the bottom of the document. They have this hash number. It's also printed on the document. You can see it if you want to. Right? You have the document and a hash number right at the bottom. Now I'll give it to you. You can do whatever you want. The only problem is when everyone who receives your document, who inspects your document, is going to use the same hash function, the same hash formula, and see whether the document, when I rehash it, I get the same number. right? So I know the formula I used to hash, and everyone knows the formula that was used to hash. The only problem is it's so all of us know what it is. I know what I used to hash it. I put this big number here, like a 50-digit number at the bottom. You take this document, hash it. If you get the 50-digit number at the bottom, if you get the exact number, that means the document has not been, or I'm kind of fairly confident the document has not been hashed, has not been altered. Because the assumption behind that is that it's very difficult to alter the document in such a way that you'll end up with the same hash code again. Right? So you cannot change a B's to A's and then expect to have the same hash code. Maybe if you
you're
change
going to
a B,
alter the doc,
go ahead.
if you're going to alter the document, why can't you also alter the hash code if you know what the hash function is?
So the
And
hash
then when you
function,
pass it on to the next person with a fake hash code.
you can. So what typically yeah, you're right. If you can, why don't you put it on the hash code too, right? So typically what they do is the hash code is something you would download. The hash code is something you would download from the known website. So there's the additional verification would be if you have that, yes, you can do that. So and we'll
That makes sense.
right? So I'll maybe next on Wednesday I'll show you how maybe this is done. So I'll describe how the public key private key encryption works, HTTPS. Right? Things that alter the way we do business. Right? The simple things like HTTPS. So this is what hashing is. Right? And we'll stop. It's almost 9. So we'll stop and we'll come back and finish it up. Right? So again, all the assignments are due by end of this week. I can wait till Monday.
Except
And
the
then,
hashing one, right?
Except the hashing one. And then you can do your midterm, schedule it, and do it around the spring break. Like take
How
your
long
spring
is
break.
it going to be?
About 2 hours, short.
2 hours.
Okay, I'll see you Wednesday.
Great.
Thank you.
Thanks so much.
Thank you.